Well, thank you ever so much for the invitation to speak here. It's a great honour and privilege to be here. I've never been to this island before. It's a beautiful and ancient place, but it's especially an honour to be able to speak in honour of Professor Fiorini. Our paths haven't really crossed very much at all in life, but they did cross once right at the start of my academic career in a very significant way, and that's what this little diagram is meant to indicate. Yes, Professor Fiorini asked a rather beautiful question, and I was lucky enough to be able to answer it. And I think that's perhaps, I mean, it was beautiful, I think. Well, the question was exactly, the question he asked was, it would be interesting to investigate whether there exist uniquely edge-colorable graphs other than the one drawn on the screen here. And it turns out there don't exist such things, provided you need at least 4 colours to colour the graph. The situation's very different with 2 or 3 colours. If you if you have a thing which is uniquely colourable with only 2 colours or 3 colours, there's quite a lot of examples and a rich structure. When it gets to 4 colours or more, this is all that can happen. There's a change in the situation. It only occurred to me as I was sitting here 2 minutes ago that that is the exact opposite of the situation I want to talk about in the lecture. So that's a sort of anti-spoiler alert, if you like. That's a rather curious way that things have changed, as far as I'm concerned, over that period of time. The time that I met Professor Fiorini was actually exactly 40 years ago, more or less to the day, which was at Tut's 60th birthday conference. And of course, we were 40 years younger then than we are now, and I'm sure, as young people do, we both thought 60 years old, you know, not even God is 60 years old. So, and certainly you know when you're that age that you will never be 60 years old. But how wrong can you be? I'm just saying that as a warning to all you sitting out there whom I know are thinking, I shall never be that old. But it's not so bad. Anyway, so Professor Fiorini, though we've not sort of interacted in the sort of unimportant way of papers perhaps and such like, he certainly had a very profound effect on my life in the way that matters, because that really did, I think it made me think I might enjoy mathematics. It had a profound effect on me. Anyway, I'm not going to talk further about that. It seems to, yes. Sorry, I'm doing this sort of Elvis Presley thing with my right hand and Donald Trump with my left, and I'm not dead sure how this is going to pan out. I might suffer from some schizophrenia at some point, but still we'll see. Okay, so what I would like to talk about is a different kind of colouring. Oh, it's vertex colouring really, but of a certain kind. So here is basic vertex colouring that we know and love, where you colour the vertices of a graph. And so if G is a graph, or more generally an R-uniform hypergraph, so that simply means the edges, instead of being pairs of vertices, as in a graph, the edges can be triples of vertices or 4 sets of vertices and such like. And a vertex colouring is simply an assignment to each vertex of a colour. This is meant to represent a set of colours. And the condition must be that no edge is monochromatic. So as far as a graph is concerned, that simply means, well, the general condition is that not every, you don't have a monochromatic edge. So you don't have an edge where every vertex in the edge is the same colour. So for graphs, that simply means you only have 2 vertices, they have to be different colours. In a hypergraph, with 4 vertices in an edge, 3 of them could be the same colour, but the 4th has to be a different colour, right? You can't have monochromatic edges. So that's what we mean by a colouring. And we have this palette of available colours, and then the chromatic number is simply the smallest size of the palette that guarantees that there is a colouring. So the smallest number k, so that there is a way of assigning colours to the vertices from the palette so that you don't get a monochromatic edge. So list colouring is a variation on that. But it seems to me actually a fairly natural variation. Here we assign initially a list of colours to each vertex. So, right, we're assigning a subset of the palette to each vertex. And the condition is to be L choosable. Given these lists, we say the graph is L choosable if there is a way of forming a vertex colouring, but the colour of each vertex has to be in its list. So you restrain, if you like, the colours that can appear at each vertex, and provided you can pick a colour for each vertex from its own list so that no edge is monochromatic, we say the graph is, or hypergraph is L choosable, and the list chromatic number is the smallest number, so that whenever you have lists of at least this size, then it is possible to make this choice. In other words, provided the lists are at least this value large at every vertex, then the graph is L choosable. So that is the list chromatic number. And I think the first time one meets this idea, you immediately think, well, what is the hardest way I could assign lists? Suppose k is 6. What is the hardest way I could assign lists of size 6 to each vertex to make the thing difficult to be choosable? Well, you'd say, let's put the same list at every vertex. That surely creates the most conflicts. And that is simply ordinary colouring with 6 colours. So what that observation means that the list chromatic number is at least as large as the chromatic number, because if you made all the lists at each vertex the same list, that is exactly ordinary colouring with k colours. List colouring allows us to have different lists of, say, 6 colours at each vertex. In your head, you think that can only make things easier to colour. Anyway, this idea was introduced, I believe, independently by Vissing and by Erdős, Rubin and Taylor. I was going to refer to these as classical papers. That's sort of how I think of them. And then, of course, I realised once again, this paper in particular is after the time that I met Professor Fiorini 40 years ago. These thoughts are really quite disturbing. So I can certainly refer to the work of Professor Fiorini as classical, because I shall refer to these things as classical. Anyhow, these guys introduced this concept of list colouring. The first observation, though, or the first thing to notice, is actually this list chromatic number can be larger than the chromatic number. This is where the subject starts to become more entertaining. And here's the sort of simplest example of this phenomenon. Take the complete bipartite graph K33. It's bipartite, so of course the chromatic number is 2. And if I were to assign the same list of 2 colours to each vertex, then I would be able to choose a colour for each vertex. But if I assign these lists of 2 colours, suppose I have a palette of 3 colours, and I assign lists in the way shown here, then it's not possible to pick a colour for each vertex in such a way that you get a proper colouring. And the easiest way perhaps to see this is to see I have 3 colours in my palette altogether. Each colour, so they're numbered 1, 2 and 3 if you like in this instance. Each colour in the final colouring can only appear on one side of the bipartite graph. It can't appear on both sides. I've only got 3 colours, so there must be one side of the bipartite graph where only one colour is used. But that's impossible, because if that colour, say, that was used on this side is 2, then here's a list where 2 doesn't appear. You're not allowed to use the colour 2 on this vertex. So you can't actually take these colours, these lists, and make the thing choosable. And so here, the list chromatic number is at least 3. It can be bigger than the chromatic number. And in fact, this phenomenon extends if you have a larger bipartite graph. Suppose you take KMM, where M is at least 2k minus 1, choose k. That gives you space to have a palette of 2k minus 1 colours. And you could take every k set of colours as a list and assign it to one of these vertices and one of these vertices on the other side. And now you can't make the choice because, why not? Well, there are 2k minus 1 colours in the palette. Each has to appear on only one side of this bipartite graph in the final colouring. And so there must be one side of the bipartite graph where only at most k minus 1 colours appear, at most half. And so, say this side, only k minus 1 colours are used, well then you've got a list which misses those k minus 1 colours. You're stuck. So what we see here is that for the complete bipartite graphs, the list colouring number is growing, even though the chromatic number is not growing, the list colouring number is growing. This means that the list chromatic number is at least k plus 1 by the definition of list chromatic number. It's fairly easy to show that that's for the complete bipartite graphs. The diagram just shown is the worst thing that can happen. Essentially, if I flip back here, k in this thing is about log base 2 of m, and that's actually the worst that can happen. And the list chromatic number of this thing is about log 2 of d. To show we've shown a lower bound on the list chromatic number, you have to show an upper bound. Look at that in a minute. But this is actually the right answer for that complete bipartite graph. And there was an extension of this by Alon and Krivolevich, here I think in more recent times, possibly in living memory, that the same value of the list chromatic number holds for almost any bipartite graph which is d-regular or roughly d-regular. That's basically what this result is saying. It actually says if you put in the edges at random, that's what happens. But essentially it's saying that almost any d-regular or roughly d-regular bipartite graph will have this list chromatic number log 2d. But the result that I want to focus on here, which is sort of at the heart of what comes afterwards, is the following theorem of Alon, which was the result of several refinements of weaker results. Not just here that for certain types of graphs, the list chromatic number is large. Alon's theorem is that for every graph of average degree d, the list chromatic number is large. You see, it's growing with d. This is clearly not true for the ordinary chromatic number, right? You can have arbitrary large average degree, and the chromatic number can still be 2 even, could be bipartite. But for the list chromatic number, it must grow with the average degree. And furthermore, that we get this lower bound, that it must grow at least at the rate of half log base 2 of d. And you can see this is pretty close to being tight, because we have examples here of graphs where it's no bigger than log base 2 of d. So this is a pretty good result, and it's within a factor of 2 of being best possible. So this is the phenomenon that is of interest for the remainder of the talk, if you like, that the list chromatic number must grow with the average degree. And the thing we're interested in is how fast it grows. So here we've got a very good, within a factor of 2 answer. But let's ask ourselves how, if we were trying to prove this, how would we try and prove something like that? And it's kind of awkward for the following reasons. First of all, you're talking about any graph of average degree d. So you have no information about the structure of the graph to help you to work on this. What is it that you have to do in order to prove this? You need a lower bound on the chromatic number. What does that mean? Well, you need really to find some lists for which it's impossible to make the choice. You need to find some lists, L, such that the graph is not L choosable, lists of size k for some k, and that'll give you a lower bound, that the list chromatic number is at least k plus 1. So you've got to produce lists where it's not possible to make the choice of colouring. And the only examples to go on at the moment are these examples here. The spirit of this really is that the best thing to do is to take random lists. Basically, that's what we were doing here. It looked like we were taking fairly carefully chosen lists. We weren't. We were taking basically all possible lists, which is much the same as taking random lists. You get a good spread of your lists across the palette. That is the only idea in town, really, as to taking bad lists. So that is what we aim to do. How might we prove Alon's theorem, then? Actually, it was quite a cunning proof. I'm not going to show you Alon's proof. But to get a lower bound on the list chromatic number of a graph, let's decide that the best thing for us to do is to assign the lists of colours at random from the palette. But then we're faced with a problem. How are we going to show, now that we've assigned these lists, how are we going to show that there is no choice of colouring from those lists? Because we have no information about the structure of the graph. Well, here's a sort of idea that we might think about. I feel rather ashamed coming to Malta with artwork of this kind, because I know there's rather better artwork floating around. But so bear with me here. This is some sort of modern stuff. So this box represents, oh dear, this is a bit modern. The box represents a graph that the colours represent sets of vertices which eventually get a certain colour. So suppose we look at this graph, we say we've assigned lists to each vertex. Is it possible to get a colouring where we choose a vertex from each list and it works, we get a colouring? Well, if that happens, there must be some vertices that choose green, there must be some vertices that choose red, some that choose blue. And each, say the green vertices will form, of course, an independent set in the graph. They'll form a set with no edges inside. And so we could ask this question in advance. Suppose we decide, is it possible that this set that I pre-assign, can this set be the green vertices? Can this set be the red vertices? Can this set be the blue vertices? If we mark these sets in advance, and remember that we're choosing the lists randomly, then the question whether those lists will allow us this colouring comes down to saying, is it true that every vertex in this set has green in its list? Is it true that every vertex in this set has red in its list? And so on. Now, if it's going to be possible that we can find that the graph is L-choosable, and if the eventual colouring matches these blobs, then the lists must fit with these blobs in the way that I just said. Every vertex here has red in its list. Here has red in its list. Here I'm allowed red or green in my list. One of those must happen. But the bottom line is it's a very unlikely event. It's very unlikely that for every vertex in that picture, its list will exactly fit the blobs that I've drawn. So for any given choice of independent sets, the probability your list fits that choice of blobs is very small. That's good. The problem is, what we're hoping is we can show this way that there is no set of independent sets which the lists fit. That will show that the lists are not L-choosable. We've got our lower bound. The problem here is there are so many independent sets that even though the chances of fitting any one collection of independent sets is very small, the chances of fitting some collection of independent sets is actually not small, it's quite big. And so the argument fails. We were trying to show there's no collection of independent sets that the list fits. The argument just fails because there's too many independent sets. So that's a nice, simple way of approaching the problem, but it just fails. It's not the way Alon approached the problem. But actually, you can approach the problem this way because of a nice theorem of Sapajenko, which goes back to the 90s, possibly the 80s, which is the following theorem. And it's a statement about the independent sets in a graph. So here is Sapajenko's theorem. He says, let's take a D-regular graph with n vertices. So there is a version of the theorem that's for any graph, say with average degree D. I just have to give you an extra definition to tell you what that is, but I don't want to do that. So let's stick with D-regular graphs. Sapajenko says then there's a collection of subsets of the vertices of this graph, and this is any graph, remember, and these subsets are called containers with the following three properties. And the first property is that every independent set is inside one of the containers. So I have my collection of containers. Given an independent set, there is one of these container subsets which contains the independent set. That's why we use the word container. So these things contain the independent sets. The second property is that the container sets are not too big. And the way to think of this is that the container sets aren't really any bigger than an independent set. In a regular graph, an independent set can't be larger than half the number of vertices, all right? Because if you say it's 10 regular, each vertex in your independent set gives off 10 edges, and they have to go to the outside and be absorbed by the other side. So an independent set won't be any bigger than half n, and this thing says the container sets are not much bigger. So in a way, they look a bit like independent sets themselves. But the third property is very important. The number of container sets, the size of our collection of containers, is small. Now, some constant here, let's ignore it. This is basically 2 to the power n over d. There can be a huge number of independent sets, like 2 to the constant n, 2 to the half n. That's why the previous argument failed. But here, if D is large, the number of sets in my container collection is much smaller. And that's, I can then use this Sapajenko theorem to go back. If I just remind you of the previous argument where I tried to kill off L-choosability using independent sets, I can do the same argument just using containers. You see, if I go back to the random lists, I can draw blobs, not this time independent sets, but draw containers. And it's still true that the lists must fit into the containers. Why? Because of the first property. Each color is an independent set, so it's contained in a container set. So the lists must fit the container sets. The second property says the container sets are not much bigger than independent sets. And that means that my argument that says it's difficult for random lists to fit independent sets will work just as well here. It's very difficult for lists to fit containers. And the final property is what makes the whole argument work. There are very few containers. And so the chances of fitting a particular collection of containers is very, very small. There aren't many containers now, so the chances of fitting any collection of containers is small. The argument works. We have a proof of Alon's theorem. So, you know, that's what the happy banana was meant to indicate. So these containers give us a very easy way of proving Alon's theorem. I'll say a bit more about the numbers you get in a minute. But essentially what we want to do now is think, well, does this extend to hypergraphs? Again, this is not historically how the thing worked, but it's one way of looking at it now. So what sort of hypergraphs are we interested in? Well, as I said, a hypergraph is an object where the sets are, the edges are subsets of the edges. Think of it as being a fixed size. So, I mean, a projective plane is a hypergraph, but the edges are subsets of size square root the number of the edges and vertices, and that's sort of beyond the scope of what I'm saying. So think of the edges here as being triples. Actually is good enough, because the first and canonical example is if you take a Latin square graph. So a Latin square hypergraph is an object where you write down a triple, one for each row, column, and the label that's in that entry in your Latin square. That gives you a three uniform hypergraph, which is simple in the sense that a simple or linear hypergraph, no two edges have more than one common vertex. List coloring problems for hypergraphs which aren't simple tend to become simpler. So we stick with this condition of linearity or simplicity for things. So a Latin square graph, yes, the vertices would correspond to the vertices for the rows, the vertices for the columns, the vertices for the labels. It's a three-partite, three-uniform hypergraph. And the list chromatic number of Latin square graphs was investigated by Haxel and Pei, and there were some further subsequent results along these lines. But if we wanted to prove a general result akin to Alon's about the list chromatic number of any hypergraph of average degree D, given what I said about Saperjenko's easy approach, the easiest way to do it would be to have a hypergraph generalization of Saperjenko's container theorem, and a version of that is what's presented here. So the particular version I've got is one due to Saxton and myself. There is a version very close due to Balog, Morris, and Samity. So these things were recently discovered, that containers exist for hypergraphs. But the particular version that's relevant to us here for colouring is this. It's basically the same statement if you look at it, except we've replaced the word graph here by hypergraph. And so the conditions are the same. For every independent set, there's a container set that contains it. Every container is not quite the whole vertex set. It's bounded away from the number of vertices. And the number of containers is 2 to the power n times something which is smaller than 1. It's sort of going down to 0 with D. I've grayed these bits out because the details here aren't of particular interest. Really all I'm saying is it's possible to prove a container version for hypergraphs of Saperjenko's graph theory container theorem, and therefore by the same argument we can just plug that in and get a lower bound on the list chromatic number of any hypergraph, a simple hypergraph or linear hypergraph. And so here is a theorem then that the list chromatic number of a hypergraph, our uniform hypergraph, is at least this large. And if you want to do things for non-regular or non-simple, you can do stuff if you want. But let's just take this for regular and simple. So at this stage, where are we? There is Alon's theorem for graphs. We've now got this theorem for hypergraphs. And the question we would like to ask now is, how good is this as a bound? You know, can you improve this bound? And I suppose the reason I'm interested in that particularly is because, in a way, it's an indication of how good containers are at attacking this list colouring question. So for the rest of the talk, this is really what we would like to ask ourselves. Here we have a lower bound on the list chromatic number of every hypergraph. This includes the case R is 2. So it includes the graph case. And the question is, how good is this bound, or can you improve it? Well, the first thing to look at is the case R is 2, the graph case. And you can see if you put in R is 2 here, we actually get 1 plus little o1 times log base 2 of D. And that actually improves Alon's bound, because that was half plus little o1. So we've doubled Alon's bound, and as we know, that's best possible, because a complete bipartite graph achieves that. So we have closed that gap. We have the exact right answer now for graphs. So that's a promising start. So the next thing might be to look at hypergraphs. What about 3-unit? What about the Latin square graph, right? What can we say about that? Does this help us there? So for R is 3, our theorem is saying for every 3 uniform simple hypergraph, the list chromatic number is at least half log base 3 of D. Is that tight? So that question is there a 3 uniform hypergraph whose list chromatic number is as low as this? Or the other side of that same coin is that if not, then this theorem is capable of improvement when R is 3. So we look around for examples of 3 uniform hypergraphs which might give us a low list chromatic number. For example, this Latin square graph, well, it gets pretty close. You see, this Latin square graph is 3-partite, so it's a subgraph of this thing, which is the complete 3 uniform hypergraph. And that thing does have, akin to the bipartite graph that we showed right at the beginning, had list chromatic number log base 2 of D. The 3-partite version has list chromatic number log base 3 of D. It's quite easy to show that. And since this Latin square graph is a subgraph of the complete thing, that has list chromatic number at most log base 3 of D. So we have a simple hypergraph whose list chromatic number, once again, we've got a gap of 2, haven't we? From the lower bound is half of this upper bound we've got. Our difficulty here, compared with the graph case, is that this easy to work with complete graph is not simple, and we're interested in simple subgraphs, and it kind of gets harder to work with those because they can be harder to describe. I mean, how do you describe a general Latin square graph? Not quite so trivial. So what are we going to do here? So the aim now, for a minute or two, is to try and think of hypergraphs, and let's just think of 3 uniform hypergraphs, that might have low list chromatic number and might achieve this bound. And actually, the Latin square graph is a pretty good candidate. So what can we say about these things? Okay, here is a general definition. I'm not sure this is written it's not even a definition. I don't know, it's just describing the universe we're in. But suppose we think of R-partite, R-uniform hypergraphs. So this means the vertices come in R classes, which are disjoint. Let's say there are n vertices in each class, and the edges have 1 vertex in each class, right? And so the edges are of size R, the things R-partite. Given a set of vertices, it's handy to say how many vertices there are in that set X, which lie in the ith class. So we'll write Xi to mean the subset of this set of vertices which lie in the ith class. Now here I've written down 2 properties that a hypergraph might have. Don't look at them too closely, is the first piece of advice. But what is it that these 2 properties are saying? They're really trying to say, in a typical R-partite hypergraph, and possibly a Latin square graph, a typical Latin square graph, what might the independent sets look like? What sort of shape have they got? They're a subset of the vertex set, so they have some in the first class, some in the second class, some in the third class. What sort of shape do you see? Well, it turns out that what matters is the product of these sizes, the number you have in each class. That somehow is relevant. That product can't be too big if you're independent. That's what this property NR is saying. The product of those things can't get too big. There's a corresponding property here, DR, that says if you have any set whose shape is no worse than an independent set can have, then that set itself might not be independent, but it's certainly going to be sparse. So sparse and independent sets always have the same sort of shape in a typical R-partite hypergraph. This remains true even in, if you go back to graphs and think of bipartite graphs, typical bipartite graphs, there are constraints on how big an independent set can be when it meets both sides, and this product thing is constrained somehow. So this is just a generalization of a simple sort of observation. But here is a theorem that Ares Marua was a student at Cambridge and myself proved, that if you have a hypergraph which has these deterministic properties, if you have these two properties, then we can tell you exactly what the list chromatic number is. It's exactly some constant depending on R times log base R of G. Now, so what this is telling you is the list chromatic number of typical R-partite hypergraphs. We're hoping that though this will give us, remember this is our lower bound for the list chromatic number, we're hoping that this will give us examples of hypergraphs whose list chromatic number is so low that it matches up with this number, and now we know we've got an exact description of the situation. Now, I said we can tell you exactly what the list chromatic number is. There's this constant floating around in the middle of the theorem, and of course, the constant is the only thing we're interested in. So in some sense, I've told you nothing unless I tell you what is this number here. And in particular, is it the same as this number 1 over R minus 1 here? This number here is, I shall now tell you what it is. It comes from a coloring algorithm. So suppose I want to get an upper bound on the list chromatic number of a Latin square. I need an algorithm to color the Latin square. Given somebody gives me lists on the vertices, I need an algorithm to produce a coloring from those lists. In other words, I need to show the graph is choosable given those lists. And here is an algorithm for coloring such a graph, which seems to work, well, it works as well as it can work. So it's a fairly simple sort of idea, a thing called a preference order. So a preference order, if you fix the number R in your head, let's fix R equal to 3, a preference order on the numbers 1 up to M is a collection of 3 total orders on that same set. Well, here I've started with R is 2. This would apply to coloring graphs, if I wanted to color bipartite graphs. Just take two orders on the numbers 1 up to M. It doesn't have to be this type. Any 2 orders count as a preference order. Here I've chosen an order where, think of the order of preference as going from the top down to the bottom. And here's another order, which is the same things but in reverse order. So those 2 things together are called a preference order for R is 2. Here is a preference order for R is 3. So this is a bit more weird looking, but rather interesting in some way. So here I've said the number of elements I'm ordering is a multiple of 3. Let's look at this first order here. I've split the numbers 1 to M into 3 groups by colors, just to help you understand the other 2 orders there. So here the green things were the blue one, the blue group and the red group. And you can see that the remaining 2 columns, what we've done is cycled round the groups. So the red group has moved to the top, and the green and the blue have moved down. And then in the next one, again, the blues have moved to the top, and the greens and the blues have moved. I said the wrong words there, but I think you can see that the groups of colours go in a sort of cyclic way. But there's a twist to that whenever you write down the bottom group, you do it upside down. So you see here, the blue group, 2k down to k plus 1, Here's 2k down to k plus 1. But when it appears at the bottom, you flip it. So it becomes k plus 1 down to 2k. And that's happening each time. The bottom group gets flipped upside down. Now, all I've shown you here is a rather bizarre way of writing down 3 total orders on the numbers 1 up to m. The reason I've shown you this, I could show you any 3 orders, but the reason I've shown you this one is that it's the one that works best, as it will turn out, for the colouring algorithm. So what is the colouring algorithm? If you have such a preference order, how does it give you a colouring algorithm? Well, it gives you a colouring algorithm in this way. Suppose we have our Latin square graph, so it's a 3-partite, 3-uniform graph. And suppose we have our lists assigned to the vertices of size L, say, then the algorithm is as follows. Suppose all the colours we've used altogether is a total of m colours. Well, we randomly number the colours 1 up to m. So they might be red, green, yellow, whatever. Just randomly number them 1 up to m. Then take your favourite preference order on m things. So, we might take the one I just showed you if we're doing the Latin square graph. And then the algorithm says, if I am a vertex in the ith column, the ith class, the colour that I choose for myself from my list is the one that's most preferred in the ith order of preference. So to go back here, if I'm a vertex in the second list, in the second class of the Latin square graph, the colour I will choose is the one that comes highest in here that is in my list. Okay? So the question is, does that work? Does it give you a proper colouring? It gives you some colouring, but you might get monochromatic edges. I've tried to grey out this final statement here, that you add a twist to what I've just said. I'm not going to talk about that, but there is a little extra twist needed that gives the improvement that makes it better. So the only observation you need to make is that you can, well, you don't really need to make this observation, but let's make it anyway. The probability that a vertex, say in the second class, chooses the colour green is the probability that that vertices list came at green or below in the second ordering. And if green was 1/3 of the way up the second ordering, the probability of that happening is 1/3 to the size of the list. And so you can quite easily compute the probability of getting a given colour, and then because we have some information about sparse sets in our hypergraph, that's this property dr, we can work out this set of green vertices can't be too big. And that gives us, let me not say any more. From here you can say, if the lists are big enough, this algorithm will work. That's what we're trying to do, to get an upper bound on the list chromatic number. And that's where this number gr comes from. It relates to properties of that ordering I just showed you. So, to finish off here then, how does one get that relationship between the list sizes and the list chromatic number? It's something to do with the preference order, and we join them up by assigning a value to each preference order. So if I can just, yes, I mentioned in the previous thing, you don't choose any preference order, you choose the best one you can for the algorithm. How do you know what a good preference order is to choose for the algorithm? It's one which has the lowest possible value, where the value is this thing. It's to do with the products of the heights where the various numbers appear in the orders. That's sort of what joins up the definition and the properties of the graph you have. We don't need to explore exactly how you assign a value to a preference order. There is a way of doing it, and then you just pick the one which has the minimum value. And this number f of r is the minimum value of all preference orders. So the idea, if you want to use this algorithm, is to pick the preference order that has the minimum value. Here is the number for 2, here is the minimum possible for 3. The preference order I showed you has this minimum value. For 4, things get a bit more entertaining. Actually, this refers back to what I said at the beginning of the talk. It turns out with this algorithm, the situation is very simple to describe for graphs, and even it turns out for 3 uniform hypergraphs. But when you get to 4, everything hits the fan, and it's not quite clear what's going on, but that looks like it's the value of f of r. I'll skip over this slide, which says that there is a way of relating a lower bound to the list chromatic number of Latin square graphs and such like, in using preference orders again. It's slightly strange because preference orders was designed to give you an upper bound, but you can use the same ideas to produce a lower bound. And so at the end of the day, we're left with this situation. We have a lower bound for list chromatic number of all hypergraphs from containers. We have this precise answer in terms of preference orders for almost all examples that we think are likely to give us decent lower bounds. And so do these numbers agree? That's what we want to know. Well, here are the values of f of r, the values of the preference orders. What is g? It's just the log of f. That's just how the maths works. And so here we see g of 2 is 1, and that means the number coming out for graphs is 1 log 2 of d. That's nice. G of 3 is a half, so the number coming out for hypergraphs, we have hypergraphs whose list chromatic number is half log base 3 of d. Perfect, that was our lower bound, so we're tight at 3. For 4, we'd like a third log base 4 of d, but we don't. We have this funny number here, which is bigger than a third. And so the bottom line to all this is that it would seem that the container arguments are telling you the exact answer about life for graphs and even for Latin square hypergraphs, but exactly the opposite to the original Professor Fiorini question. Once you get up to r is 4 or above, life doesn't get simpler, it gets more complicated, and we don't quite know what's going on really. So there we go.